All right, acetals and hemiacetals. So, um, ROCORs and ROCOHs. So, what do they actually look like? These C's in the middle have other bonds to them in both cases. So, here's an acetal. What am I talking about? The ROCOR. This is the first ROCOR. So, it doesn't really talk about what else is on that carbon skeleton. This could be an H or a carbon. That could be one of them has to be a carbon. Um, In any case, how are they formed? They are formed kind of the same way that hydrates are formed, but because we can control the quantities of the different things, we can kind of push the equilibrium one way or another in a very similar way to the imine enamine stuff that we've talked about. So, how does this reaction work? Well, the alcohol that is essentially going to be connected at some point to the carbonyl carbon is attracted to that carbonyl carbon, but it's not a very good nucleophile yet, and you essentially need a stronger nucleophile to have something add in there. So that's what the acid catalysis is. So essentially, there is going to be some acid around. I'll draw it as H3O plus, and that acts to protonate the carbonyl carbon. And again, I'll note that this is far to this side, but when that does protonate, because that oxygen is now positively charged, it's pulling a lot of electron density away from that carbon, making it even more electrophilic. And at that point, we are in a solution of that alcohol, the methanol, and that methanol can then add into that carbonyl carbon to form the first carbon-oxygen bond. So that would provide us with this intermediate, where essentially now we're going to get different proton transfers that aren't favored one way or another. They're equally it's basically a 50-50 type thing, right? So this oxygen has 2 bonds, it's neutral. This oxygen has 3 bonds, it's neutral. It's positively charged. So if we transfer a proton intramolecularly like that, we see that now we again have one oxygen that has 3 bonds and is charged, and another oxygen that is neutral. So essentially, it's just kind of by chance which of those oxygens has the positive charge at any given time. But essentially, these equilibrium arrows are true. This could have pushed this back out, and we could have gone back to here. But given that there is enough excess of this HOCH3 around, enough of the methanol, the opposite should occur, where essentially we kick out that water leaving group to provide this oxonium ion, which just like this was really electrophilic, this carbonyl carbon is really electrophilic as well. So the water could add back in. That's something that certainly could happen. But again, we're probably in methanol as our solvent. So there are probably there's probably a super heavy excess of this for every one of those. So the likelihood that this comes into contact with that versus the water molecule is pretty good. So essentially the second equivalent of methanol can add to the carbonyl carbon there. We would then form the O carbon bond, the second one. We have our protonated oxonium. That oxonium is needing to become neutral to get to the final acetal intermediate, and that can occur by reforming our catalytic acid. The water could grab that, another molecule of methanol could grab that. We'll show both. What's the more likely scenario? It's more likely that the methanol is doing it because there's just more of it around and they're very equal in their basicity. But essentially that's the last step. We went from there to our acetal. and that provides the mechanism. And go through each of these steps. Talk out yourself A, B, C, D with the steps, reasoning out why it may or may not happen, to really lock this mechanism into your brain. And again, hopefully it doesn't seem totally new. These are the same steps that occurred in that imine formation, in the enamine formation. So the only real new thing is that now it is an oxygen and an oxygen instead of an oxygen and nitrogen. So more on this in a minute. All right, so should acetal formation occur? What about it entropically? We started with 3 molecules over here, 1 molecule of aldehyde, 2 molecules of alcohol. We ended with 1 acetal and 1 water. So essentially we are going from 3 molecules to 2. That is less random, so we are entropically disfavored. What about the enthalpy, so the bond energies? Again, it's kind of the same situation as the hydrates. We're pretty neutral here, probably very slightly favored, but for all intents and purposes, the maybe slightly favoredness here doesn't make up for the entropically disfavoredness here. So we'll call it neutral because it is just so slightly favored. So essentially, this is a disfavored process. Again, can we push it to the right side? Can we push it to over here as the products? Maybe. We would have to really swamp it with equilibrium, but it is going to be kind of a challenge. And that's kind of why the equilibrium arrows are like that, with acid catalysis causes it to fall apart just like it causes it to form. So really it's all just based on the quantity of each thing that you have. If there was a huge excess of water, it would push it this way. If we're in this as a solvent, we'll push it to this side to some degree. So how can we make acetal formation more favorable? That's what we're going to talk about next. How can we make acetal formation more favorable? Well, what did we have a moment ago? We had 1 aldehyde mixed with 2 molecules of alcohol. So what's changed here? Now we have an aldehyde, and we have 1 molecule that has 2 alcohols on it. So instead of going from 3 molecules on this side to 2 molecules, now we have 2 molecules, and if both of those act as the alcohol, the individual alcohols, we should be going from 2 molecules to 2 molecules. So I'm not going to go through the mechanism here, but it works the exact same. It's just that the oxygens are tethered together, but essentially these are going to switch out for the double bond of the oxygen here, and they're going to form a cyclic acetal. So that oxygen and that oxygen are those 2 oxygens, and we got rid of a water molecule. How does this help us? Well, last time we were entropically disfavored and enthalpically neutral. Now we are entropically, neutral, right? Because we went from 2 to 2. And we are also, let's just say delta H, so enthalpically also roughly neutral. So essentially, we've changed the game by making the oxygens of the acetal both part of the same molecule, and that is going to make this more favored. So that is a good thing. So that being said, we're still kind of neutral. So if we want to really form this acetal, how can we do that? And to do that, we're going to use Le Chatelier's principle. And this is on the bottom of this page for the course packet. It says the reaction is still in equilibrium, but how can we drive it to one side? And it says Le Chatelier's principle. Whenever a system in equilibrium is disturbed, the system will, underline, adjust itself to reestablish the equilibrium. So what does that mean? It'll adjust itself to reestablish the equilibrium. I'm going to set something up on the board, and I'll be back in one moment. The system will adjust itself to reestablish equilibrium, Le Chatelier's principle. So how does that help us make more of our acetal? Well, what if we started with 2,000 total molecules, 1,000 of that, 1,000 of that, and we're just going to say we said everything's kind of neutral. So at equilibrium, we'll say that there's 500 of those, 500 of those, 500 of those, and 500 of those. So how can we push the reaction forward? And the way we do that is remove one of the things on the product side. So say we remove the water. So this got removed. So we remove the water. That means we had 500 of those, 500 of those, 500 of those, and 0 of those. Well, now we are going to re-establish equilibrium. Re-establish EQ. And what does that mean? Well, essentially now we had 2,000 molecules, now we have 1,500 molecules. And the equilibrium position of this is half of it over here, half of it over there. So we have a total of, these are the total numbers of molecules we have. And essentially to get the number of molecules on this side to equal the number of molecules on this side, these are going to drop to 375 and 375. This stayed, so the 125 that got pulled out of here means that we have 125 waters over here and 625 product molecules. So again, the organic molecule is what we want. That's what we're trying to make the acetal. And we reestablish the equilibrium to pull more of it in here. Well, what happens now? Well, we get rid of the water again. So we pulled away water, so minus H2O here, minus H2O here. That means we had 0 of that. We had 625 of that. 375 and 375. What's going to happen now? Well, the same situation is going to occur again. Every cycle that occurs, we're pushing a little bit more and a little bit more over to that product side. And we will be able to do this until we've consumed all of these materials over here. So that's how we use Le Chatelier's principle to push the equilibrium forward to the acetal. And what we actually use in the laboratory to do this is something called the Dean-Stark apparatus, and there's a nice color picture in your course packet. And it says the Dean-Stark apparatus allows us to remove the water from a reaction and force the reaction forward. So how does that work? Well, we boil the reaction right there, and essentially that refluxes it, right? So the vapors go up there, over here, and then they hit the condenser. The water condenser makes everything drip down into this collection vessel. And that collection vessel will then have a mixture of our water and our organic solvent, because this is actually run in an organic solvent. The most standard organic solvent that is used is benzene. And actually, yeah, that's what it says right here. Benzene. So essentially at that point, the benzene, the lower level contains the water, so essentially the benzene and water separate, and the upper layer contains the benzene. And as more of the solvent comes up here and drips back down, we're never going to become totally dry in our reaction vessel, because the benzene will just condense and drip back down into the flask. So that's how a Dean-Stark apparatus works. It allows us to selectively pull out our water and let all the other reaction components drip back down into the reaction flask for this stuff to continue to react together, pushing the reaction forward, giving us more and more product. So that is that's how we are able to utilize that principle, Le Chatelier's principle, to drive our reaction forward toward the acetal.